All right, let's get right into it. Today, we are building production-grade agentic AI, and we're doing it from scratch. That means no magic frameworks, no high-level abstractions, just pure, unadulterated code in Go and Rust. Why? Because the future of AI isn't about just writing better prompts. It's about solid engineering.
So, we're all living through what you could call the Gen I paradox. You hear all this hype, right? Well, the data backs it up. McKinsey found that a staggering 78% of companies have deployed generative AI. But here's the kicker. An even bigger number, 80% of them, say it hasn't really moved the needle on productivity, cost, or revenue. So, what on earth is going on?
Well, the answer is actually pretty simple. Most Gen AI tools are just assistants. They're not operators. Think about it. They're great at answering questions, summarizing docs, and drafting emails, but they don't actually do anything. They don't execute business processes from end to end. And that, right there, is the gap we have to close.
And the key to closing that gap, the solution to this whole paradox, is making a fundamental shift in how we build these systems. We need to move towards what we call agentic AI. And no, these are not just smarter chatbots. These are autonomous systems that are literally designed to pursue goals and achieve real-world outcomes.
Okay, let's make this crystal clear. Your standard generative AI, it's a one-shot deal. You send a prompt, you get a response back. End of story. Agentic AI is a whole different ballgame. You don't give it a prompt, you give it a goal. It then enters this continuous loop of observing its environment, planning its next move, acting on that plan, and seeing what happens, over and over again until the goal is met. It's the difference between asking for directions and having a self-driving car that actually takes you there.
So, what's the secret sauce? What actually makes a system agentic? It really boils down to these four key things. First, autonomy. It can handle complex, multi-step tasks without a human needing to sign off on every little thing. Second, tool use. This is crucial. It can interact with the real world through APIs, databases, you name it. Third, memory. It remembers what it's done, so it learns and adapts across steps. And finally, the big one, side effects. It doesn't just give you text back. It actually changes the state of the world. Okay, so how do we actually build one of these? Well, forget all the complex frameworks for a second. At its very heart, any agentic system, no matter the language, is built around a really simple loop. This is the blueprint for everything. Let's just walk through this cycle. It all starts with step one. The agent observes the current state of the world. What's going on right now? Then, step two. It bundles up that state along with its main goal and sends it to an LLM. The LLM's only job is to propose an action. Step three is where we come in. Our code takes that proposal and actually executes a tool. And finally, step four. The outcome of that tool call, good or bad, is used to update the state. Then, we go right back to the beginning and do it all again.
Now, this is probably the most important point. This entire loop is governed by four components that we, the engineers, control. There's the state, which is a strictly typed data structure, not just a blob of text. There's the tool registry, which is just a map of functions the agent is allowed to call. The planner, that's the LLM, which only proposes what to do next. And the controller, that's our code. It's the boss. It's what actually executes actions, enforces limits, and logs everything. Let me say that again. Our system's code is in charge, not the LLM.
All right, enough theory. Theory is fantastic, but let's get our hands dirty and actually build this thing. We're going to implement this exact loop from the ground up in two of the most powerful systems languages out there. Go for its raw speed and simplicity, and Rust for its absolute ironclad safety. First up, Go. Now, rule number one for building a reliable agent, you have to stop trusting freeform JSON from the LLM. Seriously, relying on that is like giving the model a blank check. You have no idea what you're going to get back. So what do? We define a super strict tool call struct, just like this one. By enforcing types right at the boundary, we catch potential errors before they even happen and make our whole system way more predictable. And this is where Go really shines for building agents. Its native concurrency is just beautiful. So in this code, you see we have a supervisor Go routine. Think of it as the manager running the main agent loop. When it needs a tool executed, it doesn't do it itself. It spins up a lightweight worker Go routine to handle that one task. And how do they talk to each other? Through a channel, which is like a dedicated, safe communication line. This lets you handle tons of tool calls at once without ever blocking the main loop. Now, to take this from a cool prototype to a real production service, we just need to apply a few classic battle-tested Go patterns. We use context.context everywhere. That's like a stopwatch that cancels any task if it takes too long. We'll use a worker pool, which is like saying, hey, we only have 5 employees, so we can only do 5 things at once. That keeps us from getting rate limited by APIs. And we use channel-based logging to funnel all our telemetry down one safe pipe. This is how you build a Go agent that can take a punch.
Okay, now let's switch gears and look at Rust. If you thought Go's type system was strict, well, Rust takes it to a whole new level, which for reliability is a massive advantage. We define our agent state as a struct, our tools with a tool spec trait, and here's the killer feature. We model every possible plan or outcome as this agent action enum. The compiler literally forces us to handle every single case. A tool call, a finish signal, you name it. There are 0 surprises at runtime. For concurrency in Rust, we use the Tokyo runtime. And you'll notice the pattern looks a lot like Go, right? There's a main supervisor task running the loop, and it spawns worker tasks to call tools. They communicate over channels. But here is the real magic of Rust. The compiler is so incredibly smart that if you can get this code to compile, Rust guarantees that it is free of data races. That's not an opinion, that's a fact. And that's exactly what fearless concurrency means.
You know, the best practice in Rust is really simple. Don't share state, pass messages. So instead of wrapping everything in a complex lock, which is like having 10 people all trying to edit the same Google Doc at once, you just don't. You have one task that owns the state, the single source of truth, and everybody else sends it messages. It's just a cleaner, safer way to work. And when you need to wait on multiple things at once, Tokyo Select lets you do it cleanly and without any race conditions.
So I know what some of you might be thinking. This looks like a lot of work. Why not just use a framework? And that is a totally fair question. The answer, the reason we go through this trouble, is the zero abstraction payoff. It comes down to 3 things: performance, cost, and total control. Let's talk about performance first. And this isn't some theoretical benchmark. A production SDK built in Rust for the Model Context Protocol is a staggering 16 times faster than its TypeScript counterpart. 16. And it uses 50 times less memory. Look, when you're just playing around with one agent, who cares? But when you're running hundreds of them in production, that's the difference between a service that scales and one that falls over.
Next up, cost. And I mean real money, in the form of token costs. The naive way to get an agent to figure out what's wrong with your app is to just dump 1,000 lines of logs into its context. That can easily cost you 4,000 tokens of mostly noise. The smart way is to build agent-native tools. With a tool like Go Debug Agentic, the agent can run a surgical command, like asking for the value of one variable, for about 50 tokens. The cost savings are just astronomical.
And this brings us to the most crucial point of all. The era of just hacking together prompts in a Python script and calling it AI, well, that's coming to an end. Building valuable, production-grade AI that can autonomously achieve goals is a systems engineering problem. It demands a deep understanding of concurrency, state management, and type safety, the very things that languages like Go and Rust were built for.
So I'll leave you with this one final question, and it's one I want you to take back to your own projects. Look at the systems you're building and ask yourself this. Is my AI just an assistant that answers questions? Or is it a true operator that actually achieves outcomes? The answer to that question is going to define the impact you have.